Hey, hello, 102 students. I promised you guys I would put together a supplemental lecture on examples worked out from chapter 32. So, from chapter 32. And I looked at my notes here, and if we had a time in class, I would have liked to done number 5, number 17, number 20, number 39. And then maybe I'll put a slash here because I have a total of 8 problems. And maybe the best thing to do is not to try to put it all in one video, but to spread it into 2 pieces. So why don't I jump on these 2 here, or this group first. And so let's do these 4, and in the next video I'll do these 4. All right, so let's start with number 5. And I went ahead and made some hard copy printouts here of the PDF for number 5. And here it says an inductor in the form of a solenoid contains 420 turns and is 16 centimeters in length. It has a cross-sectional area of 3 square centimeters. What uniform rate of decreasing of the current through the inductor makes an EMF of 175 millivolts? All right, well, this problem kind of has 2 parts. The beginning part is to recognize that from Faraday's law, we can change. In fact, maybe I should write Faraday's law first. We can change the general idea of the change in flux to the change in current, since the change in flux comes from only the change in the current. And so buried inside of this inductance is all the pieces that go together with the flux here. Because in this problem, we're asked for what uniform rate of decrease of current through an inductor will produce this EMF. So they're asking us to solve for this. So if I say that di dt equals, and then I guess I could write that as minus the EMF over the L. Might even just drop off the negative sign because they make it very clear what decreasing. So I think they want a positive number because they want it to describe a decrease as a positive number. What uniform rate of decrease? So I'm just going to say absolute value and then drop the negative sign. And the EMF part they give us, 175, what was it, micro? Yeah, see, microvolts. So times 10 to the minus 6 volts. And then the inductance is where the kind of the second part of this problem comes in. Maybe I'll jump down to here. But if you apply Faraday's law to a solenoid, and maybe draw a solenoid over here, and so maybe something that looks like this, then N being the number of turns in the solenoid is this piece, which you heard me say that we can refer to this as the number of turns that is induced. So this is the number of turns in the secondary, because there's usually a number of turns creating the magnetic field in the primary. But in the case of self-inductance, the primary and the secondary are really the same number of turns, or really the same object, and therefore the same number of turns. All right, so the derivative of, and then so here's the magnetic flux. And so the magnetic flux would be B dA cosine of the angle between them. And for a solenoid, the magnetic field is along the axis. And so that makes an angle of 0 with the area vector. And the magnetic field from a solenoid is mu naught times little ni, where little n here is the number of turns per length. So let me just drop off the little n. And technically this would be the number of turns in the primary, but I'll just say again, the primary and secondary are kind of the same thing in this case. And then we would just have this integral of the area. And so all that comes down to, and if I do absolute value, I can drop the negative, but I would have an n here and an n here, so that's n squared. I'd have a mu naught. The integral of the dA is just the area over the length, and then we have this di dt. And maybe it wasn't necessary to repeat this. We did this in the lecture, and your author also did it. Your author said then the induction for a simple solenoid-shaped object would be equal to this factor. All right, so let's put those numbers in. And so in this problem, they tell us the number of turns, which contains 420 turns. Mu naught is 4 pi times 10 to the negative 7. And the area, and we should be a little careful here with our units. Let's talk about that. The area, they said, was 3 centimeters squared. So that would be a 3, and the centa would be times 2 squared. Centa squared to get me my square meters. And then also the length of this would be 0.16 meters. And of course, the other set of units that I didn't include here was this mu naught. And maybe the easiest way to kind of remember that is, back up here. This equation was saying the magnetic field is mu naught times the number of turns per length times current. Or if we rewrite this, mu naught would be B times the length divided by the number of turns divided by the current. And that's how I like to remember the units of mu naught. So this would be a Tesla times a meter over an amp. Okay, so in terms of my number, let's see what I get here. And so 420 squared times 4 times pi times 1 times 10 to the negative 7 times 3 times 10 to the negative 4 divided by 0.16. And I get 4.16 times 10 to the minus 4. And now if you look at the units here, this meter downstairs is going to cancel with that meter, where to go, right here. And I'm going to be left with here, for the inductance, a Tesla, a meter squared over an amp. Now, maybe it's worth remembering the Tesla is the force you would get when you have 1 coulomb of charge moving at 1 meter per second. So if you include that with a meter squared and an amp, you can cancel off 1 of the meters. Then here in the top, you would get a Newton times a meter, so that would be a joule. A joule per coulomb is a volt, and so what we have here is a volt per coulomb a volt, get that right, per amp each second. And that was our definition of a Henry. So that was a lot of steps. Hopefully it wasn't too much to get to Henrys. I probably should have wrote those in Henrys. But that was nonetheless my approach, and trying to get it in units of Henry. All right, now we can kind of finish this problem by taking it back upstairs here and say this is 4.16 times 10 to the minus 4 Henrys. Okay, maybe I better move on to page 2 here. So I'll say, okay, so here's my page 2. So my current per time, or at least the absolute value, because it's decreasing, I'm going to drop the negative, is this 175 times 10 to the minus 6, which is roughly 10 to the minus 4, and then another 10 to the minus 4. So those are going to cancel. And then maybe we should talk about our units again. Maybe I should have left the Henrys for what it means, but I'll put the volts here, and I'll come down to say, okay, so remember what a Henry is. A Henry is an inductance, so it's how much volts you get when you have the current changing. It's an amp per second. And of course, now if we write this as a compound fraction and flip it, we get amp per second on the top and volt down here. Volts cancel, and you get amp per second. So that's good. That's the units we want. That is the rate at which the current is changing. All right, so let me take this 175 times 10 to the negative 6 and divide it by 4.16 times 10 to the negative 4. And so we're changing at a rate of 0.421 amps per second. Yay! And so there's our answer. What uniform rate of decrease? So if it's always changing by this amount, you would be always producing this much voltage. And so you would get a constant voltage for your inductor because you're changing the current at a constant rate. All right, well, hope that one was helpful. Let me jump on to number 2 on my first list of 4 here. All right, let's try number 17 together. And as you can see, I printed that one also here. Here it says an inductor that has an inductor of 15 Henrys. That's huge amount. So this is a choke. And has a resistance of 30 ohms. Well, let me pause right there. One of the reasons I picked this is because remember, when you're making your inductors, you take a wire, and I guess it doesn't have to be in the shape of a solenoid. It's just kind of one of the simplest ways to make it. You just, take some kind of metal pipe and wrap the wire around it. And so this is our inductor. Okay. Now, the inductance, as we saw in the last problem, has to do with a number of factors, and a big one is how many loops, how many turns do you have in this solenoid. Also has to do with, some geometry, the size of the area and the length of it. But to get something this large, okay, 15 Henrys, you've probably got to use a lot of wire. And also, to use that long wire, you probably need to make it thin so you can fit it all on here in a reasonable amount. So that is a long, thin wire. So in addition to having an inductance, it will have some resistance. And so all of our inductors, and particularly our big inductors, or our chokes, we can't get away with ignoring the resistance. It really does add up. In this case, a significant amount to 30 amps. It's not just like 30 ohms, excuse me. It's not just like we can just say, oh, it's a wire, don't worry about the resistance. We just have to worry about the magnetic effect of the inductance. For these kind of things this big, you've got to worry about both. You got to worry about the magnetic effects, so the inductance, but you also got to worry about the fact that it has resistance. All right, so I'm going to then say that this inductor, which is 15 henries, can also be thought of as having embedded in it a resistance of R of 30 ohms. So we want to keep that in mind. Okay, so it is now connected across a 100-volt battery. What is the rate of increase of the current at time equals to 0 and at 1.5 seconds? Okay, so if you were to take a battery at 100 volts, okay, and hook it to a switch, and so hopefully this looks a little bit like our class lecture, and you hook it to an inductor L and a resistance of R. We talked a lot about this, a very simple LR circuit, and how the changing of the current when you close the switch is going to make a back EMF. Of course, the EMF comes because of the changing magnetic field, and of course the magnetic field comes from the current, and so hence self-inductance. But we came up with a couple of important points. We said, number one, when time equals to 0, you can treat an inductor as an open circuit. We said that because of the back EMF, so the EMF is minus L di dt, when you close this and you start to quickly change the current, in this case it would be an increased current, some other problems it's a decrease in current, but there would be such a quick change in the current that you would produce enough EMF that it wouldn't go to infinity. I mean, it would never be an instant change, but it would be a change that would be appropriate enough to balance whatever is driving the current in, which in this case would be 100 volts. So I would say at the moment I close this switch, there would be created a 100 volts back EMF, and so there would be no current. That is, we could treat this as an open circuit, which means no current. Now, it's probably better not to call it an open circuit, because if there was already current in there, I would say there's enough voltage created to keep that current going, and then I wouldn't call it an open circuit. But when we were doing this one, we called that an open circuit. We also said after a long period of time, where there is no more changing of the current, at least for a DC circuit, because now we're starting the next chapter where the current will never stop changing because we're going to be putting power sources that are AC. So that's kind of the difference between this chapter 32 and the next chapter 33. But in this chapter, the current can settle out, and this can become no more changing in current. It can reach a steady state, and so the voltage is 0. So we just treat it as a wire. And so what we would call then a closed circuit, or a short circuit. And so there is our 0 time and our infinite time. But we also did this. We also said you could take the voltage V, and so you can do a Kirchhoff's loop, minus L di dt minus IR, and set it equal to 0, and then solve for the current. And when we did that, let me not repeat all that calculus here, but we got out front the long-term current, which would be V over R, and then this increasing based on a time constant, and that time constant was the L over R. And so this would be the equation to use at any moment in time, including 0 and infinity. But we don't have to make it this complicated at 0 and infinity, although you can see that at 0, you would go e to the 0, which is 1, 1 minus 1 is 0, so you'd get 0 current. It would be an open circuit. And at a long period of time, e to the negative a big number is essentially 0, so you got 1 minus 0, which is 1, and then you just got V over R, and so it's essentially just a short circuit, and you just have the power supply and the resistance. So this equation is nice in the sense that it covers the current at all moments in time. All right, So there's kind of a quick little lecture review, if you will. Now we can actually do the problem at hand. Okay, so the problem at hand then says, what is the rate of increasing at time equals to 0? Well, you kind of heard me say at time equaling 0, of course, I guess we could just take the derivative of this and then set time equals to 0. But we could also just as easily say time equals to 0 because there is an open circuit, we get 100 volts. And so taking the value of the EMF in the inductor as 100 and be di dt, we can then just say it's 100 volts then divided by the 15 henries, and that would be the di dt. And of course then I would have the 100 divided by the 15 and then the volts divided by a henry. And remembering a henry is a volt per amp each second. And so unit-wise, the volts are going to cancel. This is going to turn up on its top side, and we'll get amps per second. And what is, I guess we don't need a calculator, do we, for that? 3, 6 2/3. So that must be 6.66666 and repeating. And so there is the current, at least at that moment in time. Now, maybe I should have taken the derivative because at 1.5 seconds, and there's a couple directions we can go on this one, but I don't think this is a long period of time. I don't think we can say that it's been closed for a long time and now the current is steady, which di dt would be 0. In fact, I think we can get right here this time constant, which is the L over the R, which is the 15 over 30, which comes out to be a half. So we're looking at a half a second for the time constant here. And so at 1.5 seconds, we're 3 time constants into this. So this should look something like this. It's maximum current, 1 minus e to the negative 3. And that's one of those ones I was telling you about that's probably worth, committing to memory. That's about 95%. And so we've gotten here to 95% roughly. I mean, let's just see here. E to the negative 3, yes, he's about 5%. And so 1 minus that answer is 95%. So this would be the maximum current, and we've increased up to nearly 95%. So that's why this e to the negative 3 representing 5% is a good one to remember, just like the e to the negative 1 is the 37%, and the e to the negative 5 is the 99.5%. Okay? Or, well, whoops. I subtracted it. My bad. That would be 1 minus that. So this must be 0.5%. Yeah. So if you went 1 minus e to the negative 5, you're looking at 99.5%. Or something like this, you would be looking at 1 minus e to the negative 3. So that's 1 minus 5%. Which is roughly 95%. So this is the one we're looking at. So we're 3 time constants into it, and let's get a number here. So this would be the 100 volts divided by the 30 ohms, and we're at 95% of that. And so 30 would go in there, 3 1/3, and then we want 95% of that. All right, so here's the 95%, and then 3 1/3, and so it looks like we are at a current of, ooh, and my bad. This was not the direction I originally planned on going, but I guess it'll work. Maybe I'll go the secondary plan. I was going to take the derivative of this equation. Where is it? The equation for current right here. Yeah. And take the derivative of it. See, this is the current. That's not quite what they asked in this problem. They didn't ask for what the current is. They asked for how it is changing. Okay. And so, let's see, should I go back to the way I was doing it? See, because another way, then now that we know the current, we could go current times the voltage. Current times the resistance, which would give us the voltage. So we're looking at 95% or 95 volts on the resistor. That means the voltage on the inductor is 5 volts, and that would be L over di dt. And so we would have 5 divided by the inductance, which is 15. And so when we solve this for di dt, we would have 5 volts on the inductor divided by the inductance of 15, which, let's see, if we divide by 3, we get 1/3. And so 1/3 of an amp is the way that you could do it, kind of following along what I did on the first part, where I just knew what the voltage on the inductor was, and then used this equation here that the EMF is minus L di dt. Okay. And then that's the road I decided to go after I already calculated the current and said, hey, well, we're at a current that would make it 95%. So maybe that's what the author meant. That was not what was going through my mind in the first step. My first step was to say, why don't we just take the derivative of this equation that gives us the current? And so this would be the V over R. And of course, you take a derivative of this equation. Actually, I should probably go back to here. Derivative of this equation, you get e to the minus t over tau. Let's not forget the negative sign from here. And then, of course, the negative 1 over tau from the chain rule. And so the two negatives here, I won't have to worry about, although I'm just after the absolute value anyways. And so now I get 100 over 30. My tau is a half, and then I get this e to the negative 3. And hopefully I still get that same answer. So 100 divided by 30 divided by 0.5 multiplied by e to the negative 3, and we are at our 1/3, or with some rounding there. All right, so maybe I made it worse by going 2 directions here, but that's kind of the idea of this problem. And like I said, gave me a chance to talk about real big inductors and that they have a little bit of resistance in them. All right, where are we time-wise? Oh, good, time's about right. I wanted to probably do these in about an hour. Let's go on to the third one here. Okay, so let's look at number 20. And number 20 is kind of an interesting one because we have some current coming in and we're not told too much about how this current is generated, but we're given a little graph that looks like it's 0 and it bumps up to 10 amps for 200 microseconds, and then goes back to 0. So it's kind of like this big pulse of current. In fact, let's read the problem here. It says a current pulse is fed into a partial circuit as shown. So that's why they say partial circuit. We don't really know the rest of the circuit, and so we're functioning here as engineers, and we have this part of the circuit, and we're sent this, and we're trying to do whatever it is we're trying to do with it, and anyways, we have this circuit. In this case, I guess we're just trying to analyze what would happen to this pulse of current. See, the current begins at 0 and becomes 10 amps for time 0 to a time of 200 microseconds. And then is 0 once again, so it's a little square pulse here. Determine the current in the inductor as a function of time. All right. Now, I think the real key to this is kind of a Kirchhoff's law where, okay, one thing we notice is that they're going to have the same voltage on them. They're hooked in parallel. And so if the current comes in and hits here, some of the current, and so let me call this current I naught coming in, is going to go through the resistor, let's call it number 1, and some of it's going to continue on and go through the inductor in number 2. And so using our conservation of charge, or the node rule, we know that, okay, the two currents, the one going through the resistor and the one going through the inductor, have to add up to I naught. Okay, and I naught, I guess, when the pulse first hits would be 10, and then later on would be 0. And if we then also kind of do this loop around here, maybe I'll start here, and I'd go against the current I1, so it would be plus I1R, and then minus L di2 dt equals to 0. And so hopefully this looks a little bit like the equations we saw in class, although I must say our de-energizing inductor had this form, but the currents were the same. Here it's a little more complicated because these aren't necessarily the same current. In fact, they're not. This is the current through the resistor, and this is the current through the inductor. Whereas we had it discharging or de-energizing, we had the same current in them. All right. Now, let me come back to the question here. Determine the current in the inductor. So I'd like to solve this equation for I number 2. So let me eliminate current number 1 by using this equation here. So I'm going to write equation number 1 as I naught minus I2 equals R minus L di2 dt equals 0. Okay. And so now if I rearrange this equation, and I can get to a form that we've seen for our differential equations, that is, can we make it separable? That is, can we put all of current 1 on, or excuse me, current 2 on one side and all of time on another? And I think so. I think if we go ahead and we bring this factor of I naught minus I2 over here to the right-hand side, we can get our I2s together. Of course, we're left with an R on the left-hand side, and I guess we have some kind of question of what we want to do with this L. Do we leave it here? In general, it makes more sense to put our constants together. It doesn't matter whether they're left or right-hand side, but I'll put it over there on the other side. And then maybe one more step to make it look like I've actually separated them. So I've got an R over L, and I'll move then the dt to the other side. All right, so now I have an equation that, of course, I'll point out, started off with, here's the Kirchhoff's loops, and here's the Kirchhoff node. And I ended up with an equation that I have to solve. It just, in this case, has a derivative in it. So this is a lot like chapter 28, where we'd have a bunch of resistors, and we'd have to solve the equation. And we used a matrix and linear algebra because they were linear equations. But now we have a derivative in here, okay? And, of course, we can now integrate. So as we integrate it, I guess I'd say from 0 to some moment in t, I would start off with a 0 current and go up to I. And so let this be for t greater than or equal to 0, but less than, because I got to remember the current's going to change after 200 microseconds. So this current I naught is actually 10 amps, at least for a while. Okay. And so now if I solve this, I get R over LT on the left-hand side. And on the right-hand side, I get a natural log of I naught minus I2. I'll say evaluated from 0 to I. And I believe the chain rule, I'll need a -1 here. Now, let me just check. Tempted to do a U sub here, but this wasn't complicated enough. I'll just take my answer and take its derivative and see if I get back here. And so taking the derivative of this, I'd get 1 over, but because of the chain rule, I would get a -1, which is why I need that -1 to balance it off. Good. All right, so I'm going to write this negative on the other side of the equation. So I get a negative R over LT. And here I get an ln of, and I'll just put in I naught minus I for the first limit, minus I naught. Which a nice property of logarithms is you can write a subtraction as a quotient. So when we get rid of the natural log, we would get this I naught minus I over I naught. And then now we've got a couple of steps of algebra to do. Bringing the I over to the left-hand side and this exponential to the right-hand side. And then maybe factoring it out because it looks so much like the one we solved for an inductor in series. And so there would be our current from our current source. By the way, for those of you in the circuits class, you probably recognize that right away because what we solved in class got this answer when we had something that was a voltage source in series with our inductor. And if we do a source transformation, we can now change our voltage into a current source, which means now our resistor, instead of being in series, would be in parallel, and that's what we have. So the same solution for the resistor in series with a constant voltage would be the same solution for a current source in parallel, and that's really what we have. And so that's kind of what the author's kind of trying to teach you, whether you're in circuits class or not, that we have a source transformation here, and so it's the same equation. So had we recognized that, we could have just started the problem right here instead of redoing the mathematics. But I think the author probably wanted us to do the mathematics. He's never mentioned kind of source transformations and what they're equivalent to. All right, so that would be the current, although really that's only half of the story, because that's the current while it is being energized. So in other words, it would be increasing like this, and eventually it's going to reach a maximum, but maybe before it gets to that maximum, we run out of time at our 200 microseconds. And then so now it's going to decay away. And so let's hold off putting some numbers in here. Let me just kind of outline it and say, all right, I'm gonna come back to that. But let's talk about now, once the 200 microseconds has been completed, and kind of look at our circuit now, and I'll come back to the beginning of this problem here. Basically, now we would have I naught equaling 0. That would be the important difference here. And so what we would have is, I guess, an equation that would look like this. I guess this would still be the same. Let me start there. I would still have my I1R for the resistor. I better draw it, because it depends how we want to look at our currents now. All right, so let's do this. So here's the pulse. Let's do the resistor here. Let's do the inductor here. Okay, so by this point, there is a significant current in number 2. And when the pulse stops, now to keep the current the same in the inductor is going to become a little power source, if you will, and drive the current around this loop, keeping it at least constant for that moment, but then decaying away. And so if we write out this equation, where we call this current number 1, and we start here and go around the loop, we no longer have to talk about a current 1 and a current 2. They are the same. That's why I kind of said, well, let's jump away from this equation, because this equation I made a big deal how they were a different number and whatnot. And we don't have to do that anymore. The other thing that's important is the current in the resistor now switches direction on us. So when I go from here to here, it's a minus IR. And then I would go with the current here, so it's minus L di dt equals 0. And that's all the equations we would need. We don't have a 1 and a 2 current anymore, so we don't need 2 equations. There is no node here. It's just a single loop. And it's a much easier equation to solve. I'll put minus IR, and then I'll put L di dt. And as I said, any of these equations that have a single differential, always look to see if they're separable. And so I will move the dt over to the left-hand side, and I'll put the di on the right-hand side. And I'll even put this I underneath it. I'll leave the R on the left. And then the L, you can decide what to do with it. You can either leave it, but I like to put all my constants together. I don't really care left or right, but I usually put them on the easier integral since they're constants. And so now I'll do my integration. And in this case, we would say, okay, this is at the end of the pulse. So let's call the end of the pulse a new time 0. We can talk about that. And then some moment in time as it's decaying away, and it has then some initial value, so I'll call it I naught. But I naught, as I pointed out, may not be the full 10 amps. You know, it was climbing up to 10 amps, and then we ran out and it started decaying. So we got to use this equation to figure out what it ramps up to. But nonetheless, let's just solve this. I think I dropped the negative sign here. Wasn't there a negative? Yeah. Okay. So when I integrate this, I get a minus RLT, and here I get a natural log of I over I naught, and then I can exponentiate it to get rid of the natural log. And sure enough, not too much of a surprise, we get an equation that we kind of expected, which is that the current would exponentially now decay away. So this is the second part of this graph as a function of time in the inductor. So it ramps up and then decays away. All right, so let's put these two equations together, and I think we can then begin to finally answer this question, which says, what was it? Determine the current in the inductor as a function of time. So here it is, and so maybe putting my answer right here, I would say from t equaling 0 to 200 microseconds, it would be this equation. And the equals 10 amps, 1 minus, and then this R over L. And the R over the L. The R is 100. The L is 10 milli. Let me write that as 0.01. And so that makes 10,000. And so I'll write this as e to the negative 10,000 t. And so there would be the mathematical equation for the currents for these 200 microseconds. And then for a time greater than 200 microseconds, and you could even say equals, because like I said, it's going to look like a graph like this. Here's the current time. It's going to come on up. And if I call up here, say 10 amps, I'm not sure how close it's going to get to the 10 amps after the 200 microseconds, but whatever it does eventually get to, that's what this equation is as it decays away. I lost it. Here it is, right here, as it kind of decays away. So I got to find that number that it ramps up to. So let me put that into here. So 10,000 times 200 micro, that's my exponent. And so let me go e to the negative 2. All right. So 1 minus that number, which is about 86%. So it looks like it ramps up and gets somewhat close, but still far enough away at 8.6 amps at 200 microseconds before then it begins to follow this equation. And so for this equation, it would be 8.6 amps E, and it's the same R and L, so it's minus 10,000. And I suppose if we want to be careful with our time factor, this equation is calling time equals to 0 when the pulse runs out, which is kind of 200 microseconds into it. So maybe we should write it as t minus 200 microseconds. And so that way, when you were actually calculating the current, your time would be 200 microseconds. You'd put in 200 microseconds and subtract 200 microseconds. That's time equals to 0 when the decay starts. So if we wanted to use the same variable in time for the first half as the second half and put it on one graph, we need to offset our solution, which restarted the clock, and make it fit there. All right, so there it is. There would be the answer to this problem as it current ramps up and then the current decays away, combining the charging up and discharging, or I should say energizing up and de-energizing. All right, well, that was a significant one. And like I said, in this first video, I said I would do 4 of them. And I'm not quite at my hour, so that's good. Maybe I can still make it within an hour. I don't know. Let's try. Oh, that I put number 20, but just did number 20. What was the 4th one on my list here? 39. So let's try number 39. Oh, and it's a black problem, so maybe we can do it and still be under an hour here. It says, in this circuit, a battery with an EMF of 50 volts, okay, and a resistor of 250, and a capacitance of a half a microfarad. A switch S is closed for a long time interval. Now, let me just reread this. Did they give me the inductance? Okay, they didn't say anything about inductance yet. All right. The switch is closed for a long period of time, and zero potential difference is measured across the capacitor. All right, well, let me pause right there. When you close this switch, it's going to get pretty complicated. We did in class an an L and a C together, and we didn't do anything quite this complicated. However, notice they're saying when time goes to infinity. And so when time goes to infinity, the voltage on here, right, the voltage on the inductor goes to 0 because di dt is 0. And of course, this just acts like a wire. So that's why there's 0 volt. And if there's 0 volts here, that means there's 0 charge on the capacitor. So that's what they're trying to say here. The switch S is closed for a long period. And 0 potential difference is measured across the capacitor. So this inductor has all the current going through it. None, of course, would go through a capacitor after a long period of time. But more than that, there is also no charge on this capacitor. That, I think, is going to become important because it says here, after the switch is open, the potential across the capacitor reaches a maximum of 150 volts. What is the value of the inductor? So we want to find the value of the inductance. That's why earlier they didn't say anything about the inductor. But notice when they open the switch, then I have this LCR circuit. And in class, we solved the one where we looked at the capacitor being initially charged and initially having the energy. And then the energy would go from electric to magnetic and then back to electric and then magnetic. And so we would have our LC circuit as this would oscillate with an angular frequency of 1 over the square root of LC. So that's what's going to happen to here. It's just to start that initial oscillation, to give it initial energy, instead of starting with the capacitor with the stored energy. That's kind of the easiest one to do, and that's why I did it in class. I just hooked the capacitor over to a battery and then disconnected the wires and then hooked it to the inductor. Here, we're going to have the initial energy in the inductor. And so that starts with magnetic energy, which then eventually oscillates. And it does exactly the same thing, and we're just initiating it, starting in the inductor. All right. But I think the magical key to this step is to realize that the energy goes back and forth between all electric and all magnetic. And so the energy magnetic is 1/2 Li squared. Then later on in time, it all goes to energy in the capacitor, which would be 1/2 half CV squared. And when it's all electric, then this would be its maximum voltage. And of course, when it's all magnetic, this would be its maximum current. So these would happen at different moments in time. They don't happen exactly at the same moment of time. This was my analogy of saying if you had a pendulum and it's swinging back and forth, as it swings over to here, it has a lot of potential energy, no kinetic. And then over here, now it has a lot of kinetic and no potential. Then it swings over here and has all potential and no kinetic. And then so it keeps going from kinetic to potential, kinetic to potential. And because of conservation of energy, we know that the maximum potential also corresponds to the maximum kinetic. And that's what I'm going to do here. I'm going to set those equal. But I want to emphasize they're not equal at the same moment in time. You don't have your maximum energies at the same moment in time. The total energy stays the same. And so you have your maximum magnetic when you have no electric, and you have your maximum electric when you have no magnetic. All right, so here's then, I think, the key to the problem that says 1/2 CV maximum squared tells us the total energy that the capacitor is eventually going to get, and it comes from the energy that's stored in the inductor because of the maximum current before you open the switch. And we're asked to solve for this L. And so maybe the first thing I'll do is just cancel off the 1/2. But they gave me the capacitance of 0.5 microfarads. And they told me that the voltage builds up to 150 volts. They want me to find the inductance, and of course maybe another hard part is the current. But remember, they said it's been switched closed for a long time, and so as we discussed here, eventually you could just think of this as a wire. So a wire has no voltage, that's why there'd be no potential on the capacitor, but it also means that you can get this current before you open the switch by just saying it would be the 50 volts divided by the 250 ohm resistor. And that would be 1/5 or 0.2. Okay, so over here I'm going to put 0.2 and square it. All right, so here is my inductance, 0.5 micro times 150 squared divided by 0.2 squared. And so that is 0.281. And those should come out to be henries. I guess I should probably check my units here. So a capacitance is in farad. Now remember, the capacitance is the charge. Well, maybe I'll put farad first. Okay. So the capacitance is farad, and then this would be volts squared. And then I'm going to divide it by the current, which is in amps squared. Now remember that capacitance is charge per volt. So we can think of this farad as a coulomb per a volt, which is kind of nice, because now one of the voltages will cancel off. And so I will have coulombs, I will have volts. And let me divide this amp into two pieces. It would be amp times an amp. Let me just leave one amp alone, but let me write the other amp as a coulomb per second. That way this coulomb would cancel off, and I would have a volt over an amp per second. And that was the definition of a henry. A henry is the voltage you get when the inductor is changing at so many amps per second. So sure enough, it's in henries. All right, good. Wasn't too long of one, but did involve a little bit of conservation of energy, as well as the inductor long term, and as well as, you know, what is the energy in the inductor and the energy in the capacitor. All right, this will be a good stopping point, and I'll do another 4 a little bit later. Take care.